in our understanding of vector surface integrals, we know that the formulas that I have on the screen are currently true, right? But I'm kind of curious, what are we actually doing when we're integrating? So maybe we can pull some things out of the formula. So this is what we have so far, but what I can do is do a little bit of rewriting, okay? And so I can write this as, okay, integral over d f of x of t, and this is going to be notation hell, so bear with me. And then I can multiply and divide by the magnitude of this normal vector. So if I do that, I'm just going to pull it apart a little bit. So ts cross tt, and then divide by the length of ts cross tt, but then if I divide, I have to multiply. So ts cross tt, okay, and then ds dt, okay, and put differently, what I can then write this as is the double integral over x of f dotted with, okay, so what I'm doing is I'm sort of lumping this and that together, and then saying that what I would be left with f of ts cross tt over the length of ts cross tt, and then d ds. Okay, and really what this is going to be giving me is, if I compare this back to what we got with a scalar surface integral, is we're really saying that this entire thing in here, this is really just a scalar surface integral. Okay, so when we compute that is to say, put it differently, when we're computing a surface or a vector surface integral or finding the flux, it's really just a scalar surface integral in disguise. Okay, and so then when we compute the scalar surface integral, really at each point on the surface, really all we're looking at is the angle between our vector field f and the unit normal vector. Okay, per this dot product. Okay, and then so the unit normal vector is ts cross tt, just for clarification, oops, over the length of ts cross tt. All right, so then, and then really when we are integrating, we just add up all those dot products. Okay, so let's do a little bit of thinking here in example 1. So we have a vector field, so it's only acting in the z direction, and then we have a unit disk parameterized so that tx cross tt points upward. So then if you need to draw this out, great, go for it. I didn't, but if you can imagine a unit disk and it's and the unit normal is pointing upward, that means it's pointing in the z direction, and we have a vector field that's pointing in the z direction. And then thinking about our vector or our flux really as this, at least geometrically, the angle between our vector field and the unit normal vector at each point on the surface. Thinking about all those angles that we have and the dot product, those should result in all positive values. So when we add them all up, the flux should be positive. Okay, So maybe spend some more time with that one. With example 2, okay, so we have a cylinder below, and you can see how it's graphed, okay, and then the vector field is given as well, x, y, z, so that's expanding out. And then we know that tx cross tt is an outward pointing normal vector. So at different places on the surface, you can see in green, tx cross tt is shown. So then if we think about the side of the flux for each point, again, you would need to take at each point, you would look at the angle between the vector field and the unit normal vector, and that angle is going to be acute, meaning that the cosine, when you do the cosine of the acute angle, you're going to get a positive number. So then when you add everything up, you're going to get a positive value for flux. Okay, so if that line of reasoning doesn't make sense to you right now, again, spend a little bit of time just and just think of the flux as the angle between the vector field and the unit normal vector. Well, I should say the cosine of that. And since we have all acute angles, we should always have the flux being positive in both of our examples here. So that's going to wrap up this example. We'll do another example of flux where we actually compute it and then think about some different things related to it in the next video.